Good afternoon, everyone from Norway. My name is Sabita Maharjan. Once again, I am an associate professor at the Department of Informatics, University of Oslo. And I also have an adjunct position, 20% position as a research scientist at Simula Metropolitan Center for Digital Engineering. Today, I'll be talking about edge intelligence. Very briefly about University of Oslo. University of Oslo is the oldest and the largest university in Norway, and it's one of the top 100 universities in the world. And again, very, very briefly about my research group. The structural hierarchy of the research group is a little bit complicated, but I'll try to explain it in a simpler form. We are doing a lot of research in a research area called energy informatics, and we belong to the group called Networks and Distributed Systems. It's a fairly large group. The Networks and Distributed Systems group comes under the section. There are many sections within the Department of Informatics, and ND, Networks and Distributed Systems, belongs to the section called Distributed Infrastructure and Security. So it's the department and then sections. Within DIAS, it's Networks and Distributed Systems, which is actually the end of the hierarchy. So that is the group. But within ND also, there are many people doing different things, and we are working on energy informatics. So we often call ourselves as a research group, but in practice, we are a subgroup of the ND, Networks and Distributed Systems research group. The full-time faculty members are us, me, Professor Zhang, and Professor Eliassen, but we also have some adjunct professors in adjunct positions who are working closely with us, Professor Jessing, Professor Uliberg, and Professor Jacobsen, for example. And we have a number of PhD students, some postdocs, some of them, Awad and Ming, they are close to graduation, also Wai Ming. Some of them are, it'll be some years before they graduate, but we're also hiring 3 new PhD students and a postdoc who will be starting to work from 2022. And we have several master students and about 4 visiting students and professors from our collaboration networks from all over the world. So that's our subgroup, basically. And I have divided my talk today into 3 parts. The first part is on energy informatics overview. The second one is edge intelligence, mainly the communication and computing perspective. And the third part is also about edge intelligence, but focusing more on privacy preservation and security considerations. But before we start talking about energy informatics, as I'd like to repeat that if you have questions as I go on, you can ask me questions or type it in the chat box. I have it open here. Also, well, I'll try to take conscious pauses in between, but I usually tend to forget to take the break, so I might as well sometimes go on. If that is the case, you can remind me to take the pause and also and ask me questions. The way I understand is in the past few days, almost 2 weeks, you've learned a lot about machine learning, deep learning, the algorithms, the mathematics behind, and also a number of applications. But probably there hasn't been many talks on networks from the network perspective, I believe. So what I'm going to introduce now, some of the terms might be new for you, but some of you might be familiar with it. So if there is any confusion about, or if you have any questions about the terms, the concepts, you can just stop me right away and we can discuss about it, okay? And I also understand that it's been a long day, 2 long weeks, a long day today. This is the last talk, I think. So I'll try to keep it interesting enough for you. All right. Energy informatics overview then. Okay, let me minimize this. So, yes. What is energy informatics? There are different ways to define energy informatics. But the way I would like to put it, consistent to the kind of work we are doing, is that it'll be a core component. It'll play a crucial role in the smart cities and will enable multiple intelligent new applications. some of the examples where energy informatics will play a crucial role or will be the foundation are smart grid, including electrification of transport or electric mobility. Also vehicular networks leading to autonomous driving, 5G, 5G beyond, 6G, and artificial intelligence as well. The context of artificial intelligence here is very interesting because you can imagine, as with every other field, artificial intelligence machine learning and deep learning can have can provide tremendous benefits in different areas, including networks. But it's not only that, it's also the role of networks in how AI will work, how AI will be able to enable systems, how AI will be able to benefit different applications and use cases. So that part is quite interesting. Yes, within energy informatics, our research activities can be, I would like to sum them up into these different points. Smart and sustainable energy systems, electric mobility, 5G, 5G beyond, vehicular networks. We've recently done some work on security as well, privacy preservation and security. And most recently, we've begun working on something called the trustworthy systems, which is a part of a new project that we have acquired. This is a very cross-disciplinary research area where we talk about digital trust and trust building, trust enhancement, where it's not only the technological part, not only data, not only AI, not only energy systems and networks, but also a lot from the social psychological perspective, from users' perspective, their requirements, their reluctance, their expectations, and so on. And not just that, also the regulation perspective, data regulation, energy law, and so on. So this is a very new area of work that we have started rather recently. Okay, all right. Then what exactly is energy informatics? What does energy informatics do? Or what kind of work do we do when we say we are working in an area called energy informatics? Let's try to look at it literally. You have energy here and the informatics. So energy systems, when you integrate informatics into the energy systems, okay, something is wrong with my slideshow mode. Let me do it again. Yes, good. So when you integrate information communication, networking, and control technologies into the energy systems, then it becomes a smart energy system, the common term used for the modern power grid, the smart grid. That is one way to look at energy informatics, and we have done quite some work in this direction in smart grid. What that means conceptually is that you have the power infrastructure, the energy systems here, generation facilities, transmission distribution networks, and also the end users here, the consumers. Market operation, it's a huge system, in fact, the biggest man-made infrastructure so far. When you integrate the ICT infrastructure into the power infrastructure, what happens is the flow of data. Now you can collect data, you can exchange data both ways. And with that, you are also enabling not just the two-way flow of data, but also the two-way flow of electricity, and now make the system smarter. What is the definition of smart? That's there, but it will make the system smarter, more efficient, and more resilient, more distributed. A number of features come in with the integration. The smart grid, the smart energy systems, they have well, a number of goals. It's a very vast research area again that has been very hot in last 8-10 years, the past decade. Still, there is a lot of work going on in this area, but the kind of work that is receiving more attention is changing over the years. So the three main goals of the highlighted goals of a smart grid for a smart grid are decarbonization, clean energy, and that's where energy efficiency also comes in. Decentralization of energy power generation, and also digitalization of the energy sector. And this kind of smart energy systems, or the smart grid, will have a number of features and needs to integrate into it different aspects. Some of them are listed here. For example, the incorporation of distributed renewable energy resources, distributed electricity trade. When I say distributed trade, that means there are the end users, they are also becoming more and more active now with the power generation capacity. Before we were consumers who used to consume electricity from the grid, but now we are becoming prosumers. That means we do not only consume the electricity, but we also produce. We as well have the resources to produce electricity from the solar panel on top of our roof, or from some other, we have a storage unit, we have an electric vehicle where you can store some power, and so on. So the electricity trade will also eventually become more distributed. And also distribution automation, system automation. That means the distribution network, you can automate it, you need to automate it in the smart grid, while previously most of it used to be manual. And a number of other features such as advanced metering infrastructure, which means the meters. The electricity meters that we used to have at home, before they used to be more or less the meters that would measure how much you have consumed. But now in the smart grid, they are the meters that can record your consumptions, but that can also communicate with the devices at home, or with the data aggregators, transmit the data to the aggregators, and can be active participants. And there's an important component called demand response management. That's where we have done a lot of work in the smart grid, which in short means making the users more responsive to the supply conditions. Before, it used to be more of whatever is the demand from the users, or whatever is likely to be the demand from the users, the supply conditions need to change accordingly. But now you're trying to make, with communication and networking technologies, you're trying to make users respond as well to the conditions of the generation and the supply side. And a number of other features here, but with all these, by integrating all these, what you expect, the eventual goal of a smart grid system is that you will have enhanced user responsiveness and grid automation with ICT. All right, then with that, I might have very well given you the impression that we focus on the power system infrastructure, the energy system infrastructure, which is actually not the case. So the application domain here is the smart energy system, but we are talking of integrating the communication and networks, communication and networking, and also control into the infrastructure. But where our work lies, where we focus on, is basically on the kind of data that is being generated by the network, and what can you do, what can you utilize that data for. For example, I'll give you an example. So in this figure, you see here, this is one household that has a number of appliances that we use every day. And it has a smart meter here. And what the smart meter can do is these household appliances, they can be connected to each other with a home area network. So is the smart meter, and it can communicate with these equipments here. But there are a number of households in the community, not just one. And it's the same story inside every household, the smart meters, and then communication going on with the appliances. There is this network and everything. But the data generated by all these smart meters, they will actually be transmitted to something called the data aggregator unit, which is at a neighborhood level. And this is called the neighborhood area networks that interfaces meter data and home area networks, multiple home area networks, traffic to higher level wide area networks. The wide area networks is the aggregation of the data from these local aggregators to a wider area network, to a wider, to a regional data aggregator, or a bigger management unit, which is mostly on the operator side, connected to the monitoring and control center. So this kind of data, how you communicate, how you collect, communicate this kind of data, and transmit this kind of data, and what can you put this data to what kind of use can you put this data to? So that is the kind of work we focus on in the case of smart grid. Yes, so smart grid, that was one perspective to look at energy informatics, and one branch of the work that we've done over the years. And now another perspective, or another parallel branch that we've been working on, these two perspectives, or these two definitions, are mainly my own definitions from mainly from the work that we have been mainly from our research activities. So I did say that you want to integrate the communication technologies, you want to bring in data and networking technologies into the energy systems, and that will make the energy systems smart or energy efficient. You can find ways to make it energy systems. Having said that, most of you or many of you might be aware that the communication and computing networks themselves are one of the biggest consumers of electricity. Data centers, they consume huge amount of electricity. Servers, they consume a lot of electricity, a lot of power. So when we say energy informatics, it's not only about making energy systems more efficient by integrating communication resources, but it's also about making the communication systems, communication networks more efficient, energy efficient. Different ways to do it, but here I put it as green sustainable energy sources, which does not literally mean you source them with renewable energy resources. That's one way of doing it, but this basically means the field where you design energy efficient communication computing networks is also energy informatics, and that's where we are working on, as well as a parallel sub area. And there are different ways to make the communication networks green and energy efficient. The first one one can think of is, okay, if you can use renewable energy resources to power the communication networks, wouldn't that be a very good solution? It would be, it is, but as easy and intuitive it sounds, as complicated it is, because of the inherent power, the inherent uncertainty issue associated with the renewable power suppliers, power generators. Another technique is energy harvesting, which basically means you harvest the energy from the environment. And there are a number of different things that you can think of in this area. It's a vast area of research in itself. Apart from using renewable power sources, energy harvesting, what we can also do is we can think of ideas, the communication computation architectures, and we can develop algorithms in order to minimize the energy consumption, even for given power resources. You can do scheduling, intelligent scheduling of tasks, for example, in the data centers, or even in communication computing networks. Even when it comes to the wireless networks, the access networks, you can still do a lot of intelligent design in the access network itself, such that the energy consumption can be minimized. And when I'm talking of energy consumption here, there are different scales. So it can be a bit overwhelming, but let me talk about two different types of energy consumptions here. The first one is the one that we are more used to in our everyday life, where you have devices, equipments, routers, switches, servers, computer servers, bigger servers. They all consume electricity, the power, but also base stations, for example. But also, that's one kind of consumption, electricity consumption, the power supply that we are talking about. But also, when you think of the communication of data, when you want to transmit the packets from one user to the other user, you need to transmit it with certain power, transmit power. And that is for one packet, of course. That will not be comparable to the power supply of a base station or a computer. But altogether, you will be transmitting a lot of packets, and that will consume a lot of power. And also, it's not one device, one mobile device or one vehicle or a few devices, but it's a lot of devices. So you are consuming a lot of electricity there. And there come in different concepts such as scheduling of users, the frequency bands, and such, where you can use smart ideas and architectures to actually minimize the energy consumption. So that's also another way of doing it. I have listed some examples here. Green data centers, making the data centers energy efficient and green. Demand response management for data centers, that's actually a way of making the data centers efficient, where you try to synchronize the operation of the data centers according to what kind of power is available, or the cheap power that's available. Also solar powered base stations in the access networks, and the energy efficient communication, which is mostly here, this one, in 5G beyond, also in 6G. And when I talk about minimizing the power consumption, or it's not always minimizing, but kind of optimizing the power consumption, because there are always constraints and quality of service requirements that come coupled with the energy consumption. So it's not as straightforward as reducing the power consumption, but what happens when you reduce the power consumption? What happens to the latency? What happens to the data rate? What happens to other things, other metrics? And how do you balance it? So it's more of a trade-off than and optimizing than only minimizing the energy consumption. It's usually a couple of different metrics that are important here. Okay, and we use different approaches for energy informatics. The conventional approaches, optimization, game theory, also machine learning and deep learning. In general, it's not always necessary to use machine learning, to use deep learning, but there are places, there are scenarios where you need to use machine learning, so that also depends a bit. And in cases where we talk about interactions, game theory is also highly relevant, but we use different techniques here. But even other than optimization techniques and machine learning, we use different technologies and paradigms that can as well play a crucial role in energy informatics and improving the energy efficiency, making the system green. And those include, for example, to name a few, blockchain, edge computing, and many more. But today we'll be talking mainly about machine learning and edge computing. Yes, machine learning, deep learning, AI, and edge computing. Is there a question here? Okay. Yes, you can ask questions. Ask them on the mic or type them, please. And I also understand that there has not been many talks on networks. So some of you might be familiar with the different concepts, but for some others, as I go on, it might be quite overwhelming. So many different concepts, new concepts for those who are not familiar with the area. So please feel free to ask me questions anytime. Okay? Yes. All right. Now we will talk about edge intelligence from the communication and computing networks perspective. Any questions so far? Okay, I don't see any messages here. So let me proceed.
I think there's a question in the chat, maybe.
Oh, okay.
Yeah.
Yes, I see one. Doesn't blockchain consume too much energy? How could using this be energy efficient? Yes. That's a very good question. That's true. Blockchain consumes a lot of energy. There are ways to also reduce that energy consumption, and there are discussions. That's a very good question, actually. But I listed blockchain as one of the technologies that we use for energy informatics. And when I said, I did say earlier that energy informatics, one of the goals is to reduce the energy consumption, but it's always coupled with other constraints. It's not only energy consumption, minimizing energy consumption, but often the goal is resource optimization. And there are other constraints such as latency and other things. But blockchain, in the case of blockchain, that we are using mainly in the context of peer-to-peer energy trade between households or between the electric vehicles. And the main focus over there is not precisely energy consumption minimization, but in that part, in the trade part, but the decentralized energy trade or decentralized management of energy, that's the main focus. And also data security. Those are the main areas that we focus on when I say blockchain. But then in the overall context of energy informatics, you are using blockchain there. But then you might as well be using blockchain in a system where we are mainly talking about electric vehicles, for example, and the photovoltaics and the power generated from the wind turbines. So in that sense, in that case, it's the green power supply. So the context here is slightly different. But you are using blockchain for a different purpose in this energy informatics ecosystem. Okay? Did I answer your question fully? Yes. Okay. How is game theory used in energy informatics? Yes, game theory has been used a lot in energy informatics. In fact, my PhD work back in 2009-10, I did use a lot of game theory based approaches for energy informatics. But it can be used for, in fact, virtually everything, all different applications. Just like now, machine learning and AI is so hot, and people are trying to borrow the machine learning algorithms to virtually every single domain. Game theory was like that too, and it still is to a large extent. See, where you use game theory is wherever there are interactions between multiple users, multiple players. It does not necessarily have to be energy informatics or energy systems, but wherever there are interactions, then you can use game theory. Game theory is one of the alternatives, not the only alternative. Now, in the context of energy systems, in energy informatics, I used it for modeling the behavior of the prosumers. You are a household. Now it has been used in different contexts, even electric vehicles, to model the interactions between different electric vehicle owners. But when you are a household, you are trying to, and a number of, okay, with game theory, you can model, there are players, actions, and strategies, and you can model who is a player, what is a player. It can be a household, that can be a player. It can also be a community with multiple households that is a player who plays against another community who is another player. Okay, so one example of it is you are a household and you are trying to save electricity by using certain appliances at certain times. But there is another household who is trying to do the same. But the thing is, you don't want to share your data with each other. You want to keep privacy as well. But then at the same time, you want to use the electricity when the prices are the least. Which is usually the nighttime. But if all the households in the community, in the neighborhood, use their appliances at the nighttime because electricity is usually cheaper there, that means if you talk about real-time pricing, the electricity price will actually become higher at the nighttime. So basically the peak hour is shifting from daytime to the nighttime, you see? So, but if some of the users use it at nighttime and some of the users use it at the daytime, okay, then there is a balance and the electricity price will still be reasonable. The cost that you pay, the total cost, not the unit price, but the total cost that you pay as the total cost of the community that you pay can be still reasonably low. But here the thing is, if all the users belong to this, are controlled by one entity, then it's an optimization problem, not a game theory problem. But when the users are themselves, but still they want to optimize their strategies independently, okay, then this depends on the interactions. What is the other player going to do when I do this? When I use it, if he's also going to use it, I will rather use it in different time slots. And the other player is thinking the same about me. And there are a number of players, not just two. So this kind of scenario, we use the game theory for energy systems. And the data, the amount of exchange and information exchange, that's the informatics part here. Okay. I hope I answered your question. Any more questions so far? All right, I move on then. Okay, then edge computing. What is edge computing and which part of the network is the edge? See, now the network is changing. The structure of the network is changing in the sense that data generation, there has been a shift in the data generation from it used to be in the cloud before, now more and more data is generated here from the end devices. And a lot of data before used to be mainly from the cloud to the users, but now it's also the other way around. And because massive amount of data is being generated here, sending all that data or part of that data, a lot of that data to the cloud, to the core network, that can lead to several challenges, including network congestion and also latency when it comes to computation, data processing, computation tasks. So we need resources, the network resources, closer to the end users. And these resources that are located closer to the end users than somewhere far in the cloud, that layer of resources, basically the edge here. Yes, these are the devices. This is the cloud, and this is the edge. Where exactly is the edge? It's not. It is somewhere close to the devices, close to the end users, not in between. It is in between, but not in the middle. It's much closer to the end devices than the cloud. Okay. Yes, and when we and that's okay. Let me just go back here. So this is the edge and the computation, the computing that is performed. Okay, I have a question here. Is it always the case? Let me read it aloud also for others. Is it always the case that game theory will provide a better utilization of the resources? Would there be a case where a static policy might be far better? Well, it really depends. It really depends. But as I said, game theory is all about the interactions between multiple players. Okay, there are different things. Multiple players and a dynamic environment. Then it's the action of each player depends on also what other players are doing. In that case, it's a natural choice to use game theory, not the only one, but game theory is one of the possible approaches. But as far as static policies are concerned, they may not always work. I mean, if you can use optimization, it depends on the scenario, the model. If the entities that we are talking about, they all belong to one particular operator or one particular community that serve a common goal, then you can use optimization. But at the same time, also for optimization, you need to have one central entity that has access to all the information related to all the users or all the players. In that case, you can use it. But then when you don't have all the information and you only have your own information and you still want to interact, and in that case, you use game theory. Okay? Yes. All right. And even in game theory, there are different kinds of games called games with complete information, incomplete information. So that's again another branch that depends. The performance that you can achieve with game theory also depends on how much information you have. But optimization is the case where you have a lot of most of the information and you have a central entity to optimize. Okay, now in this case, the edge, okay, again, the edge devices, they generate a lot of data, and in general, they have limited computation capabilities, so they need to transmit the data to the edge service. Now, not to the cloud, but to the edge service. Some of the data will still go to the cloud. The edge network, edge layer cannot exist on its own. It's 35 minutes, okay. Yes, I have kept my timer on so that I have a better track of time. Yes, so they offload certain tasks to the edge so that the network resources at the edge can be made use of by the devices here. Okay, and that kind of computing is the edge computing, and one of the very standard concepts in the context of edge computing is computation offloading, which you will also see in in almost all the work. That's at least half the part of the work that I'll be discussing later on. So I would like to explain what computation offloading is. This is an end device. In this case, a vehicle. It can as well be a mobile phone. It can be any other device, end device. And it has a number of tasks to execute, but it has limited resources and also latency constraints. So what it can do is it can execute certain tasks by itself and offload some tasks to the edge server here. This can be an RSU, the roadside unit, or some other service, and some of the tasks to the cloud. So that is one way to do it. In this case, 2 here, 5, and 3, and altogether 10 tasks, right? So that is one way to do it. But how do you know that you should be executing 2 tasks here, 5 here, and 3 here? These could as well have been 5, 5, and 0, or 0, 5, and 0, 6, and 4, any combinations, right? So to finding those optimal values for X, Y, Z, that is one of the problems to solve here in computation offloading. Okay, I have a question from Nishan. Won't there be latency problem in computation offloading? Yes, not a problem. There can be issues. Yes, when you talk about computation offloading, when you offload certain content, certain task to the roadside unit, then it will take you certain time. But what we are doing here is usually the end users and devices, they have very limited resources, much more limited compared to the edge service here, and way less resources compared to the cloud here. That's very little. So you will assess. And that's exactly the point here. You will assess if you compute it locally, considering the time for computation, and not to forget the time for communication as well, right? Computation offloading, that also depends on the communication resources that you are getting. What is the data rate that you can offload your task to the edge server or even to the cloud? That depends on the spectrum, the communication resources, and also the computation processing time here if you offload it, yes. But then that's why you have to assess whether it would be faster when we are talking only about latency. There might be other constraints as well. So whether it would be faster if you offload it here and then get back the result, or whether it would be better to execute it yourself. Okay, that is exactly what you have to consider here. And you will offload it certainly only if you will get it in a time faster than if you execute it locally. And that happens most of the time because you have very limited resources. These have much faster and much more resources. All right. But then there are, of course, that's a very simple case when we are talking about one vehicle. There will be a number of them. Many of them will be accessing the mobile edge service. So the scenario will be more dynamic and more complicated. With that, I hope I answered your question. Nishan? Yes. All right. Now that was edge computing and computation offloading. What is edge intelligence then? So edge computing is the computing part when you integrate artificial intelligence into edge computing, literally. This is edge intelligence. The examples, different examples or use cases that edge intelligence can enable. In fact, it can enable a number of applications. These are just a few to mention, but these are the applications where it will play a crucial role. Smart grid, the industrial IoT, autonomous driving, 5G, 5G beyond, and 6G. In 5G, AI is actually integrated partially in certain parts of the network. In 6G, it will be integrated. It should be integrated. At least that's how the research is going fully. Okay, my mouse is, oh, sorry. Yes, all right. So that was edge computing and edge intelligence. But why do we need to talk about edge intelligence? Why don't we talk just about AI? Isn't it? You've been learning about AI. Many of you have been working on very complex problems using AI. So why don't we talk about just AI and why edge intelligence? Why not only artificial intelligence? I would like to talk about two different aspects here. The first one is that AI, artificial intelligence, can act as a tool to deal with large-scale complex networks to capture the hidden patterns within the network. You see, and this is a very important point to understand here, because this is what we are going to do. This is what I'll be, this is the kind of work I'll be walking you through in the next couple of slides, many slides actually. So we use AI to detect the hidden patterns within the network and for better resource utilization or for resource optimization. So AI is definitely a tool. And this is, I believe, more intuitive. As AI has been used as a tool for many different dimensions, so is the case. We are trying to borrow it for the case of networks as well. But at the same time, what I would also like you to understand is it's not only AI for networks, but what role does network play in AI, in how AI algorithms, deep learning algorithms can be executed, whether or not they can be executed. How does network facilitate the data processing and the algorithms? So that is also another part. A massive amount of data that can be processed and utilized close to the end users in an edge network, which is the concept of edge computing. And that also facilitates a lot of a new paradigm of utilizing AI close to the users, not having to communicate all the data to the core, and that makes the scenario very different. Okay. Yes. Now I'll talk very briefly about some applications of artificial intelligence in smart energy systems. In fact, it can be used as a tool for many different applications within the energy industry, for smart energy systems. But we've done some work on forecasts of power generation from the wind turbines, from the solar panels, which is really important because, as I mentioned earlier, there is an inherent uncertainty with the power sources, the renewable power sources, how much power they can generate. Even though you have weather data and even though there are many models that where you can input the wind speed, and that will give you as an output the amount of power generation from the wind turbine. But with AI, they are becoming better and better. The precision is increasing. So that's one area where it has been extensively used, and not excessively. So forecast, generation forecast, and at the same time also demand forecast. How much the users will be needing, how much power they will be using. That's also quite stochastic in quite a stochastic pattern. So the AI algorithms have been used excessively there as well for distributed electricity trade, for residential energy management, and also for monitoring of the monitoring and coordination of the distribution networks. And also in the smart grid, there is something called, okay, my chat is hiding, this chat box is hiding some part of my slides. I'm not sure how it is appearing for you guys, but you only see my slide, I assume, right? You don't see the chat box.
No, yeah, only the presentation.
Okay, good. So see here, this is the smart grid and smart buildings and industry, that's okay. But then you see something called grid edge here, the green part. This is also green, well, this is a bluish green, let me say. The grid edge, there is a grid edge here, which basically means the edge part, the consumers, the prosumers. And they also have certain intelligence, which is actually there is a term called energy intelligence, but today I'll not be talking much about it. I'll be focusing more on edge intelligence for the network side. But the energy intelligence is a new term sorry about that. Okay, energy intelligence is the new term for that represents the intelligence at the grid edge. So here you have this greenish bluish green part called grid edge here in the smart grid. You also have a little bit of it in decentralized energy generation, which basically means the prosumers, the consumers who now have some of their own power generation from a solar panel or from a small turbine. You also have it here in the storage. The electric vehicles are a standard form of storage now, and additional battery. Renewable energy management, the users are also playing an important role now, but mostly these areas. Also electric vehicle charging, of course, the prosumers who have electric vehicles. The rest is mostly the utility and transmission distribution networks. But in the smart grid area also a lot of developments are happening, and a good amount of research is going on in the grid edge and energy intelligence. All right, some examples now very briefly. The 46 minutes, okay, I should probably hurry up a bit. This is one of the recent applications in smart grid using UAVs for edge intelligence. So what UAVs do is, so you have the wind turbines, they are usually deployed offshore, they need to be constantly monitored though. And these UAVs, they can take pictures, they can use other data, and for processing before they needed to transmit the data somewhere far off. But with edge computing and edge intelligence, when the UAV is equipped with certain storage and certain computation capability, it can make use of algorithms to actually not just monitor, but also to make decisions for these relevant decisions for these wind turbines. For example, detection of wind turbine, the cracks on the turbine blades. That's one very popular application nowadays, and these are cheap, economic, and very good solutions. One of the solutions, popular solutions. Okay, so to keep it brief, I just gave you a few examples there on the smart grid part. Now I'm coming to the network part. We talked about edge computing. When we say mobile edge computing, again, you look at the term mobile. When we add mobility to the network, then it becomes a mobile edge computing network from edge computing network. And in this case, the edge server is a mobile edge computing server, MEC server. You have the terminal here, and what it basically means when you say mobile edge computing paradigm is that these terminals are mobile. They are not stationary terminals like in the smart grid. In smart grid, most of the households are stationary, right? In this case, they are mobile. And the mobile edge computing server can be located near a base station somewhere in the access network. Okay, something is wrong with the slides. Yes, they are located in or close to the access network. We have done extensive amount of work in mobile edge computing. This model, this figure is from one of the papers from 2016, which is also one of the hot papers and highly cited paper until now. And this, we were the first to study and coin the term mobile edge computing. And this has been accepted by the research community as one of the standard models and in the studies that followed the study of ours. Yes, and mobile edge computing has tremendous applications. You will notice that I'm quite fond of this term called smart cities, although this may be interpreted differently by different people. But the reason I like to keep it as smart cities is because it can virtually include all different emerging applications and new applications to come. So this is the edge network, edge resources here. This is the core network, the cloud. And this is the end users and the applications here that are enabled by the mobile edge computing paradigm. And you will see here the applications range from transportation, different applications within transportation as well, for intelligent transportation services such as advanced sensors, vehicular applications, self-driving, traffic control, vehicular safety, to the industrial IoT, smart grid, from grid state monitoring and power management, either market management or distributed trade. Mobile edge computing can serve as the underlying infrastructure or foundation for many different applications, but not just transportation and smart grid, also agriculture, also healthcare, although these are not the applications that we are focusing on, but virtually many applications here. That's why mobile edge computing is a very hot and happening topic in our area from past 5, 6, 7 years, and it continues to be so. And when I say mobile edge computing, we talked about the edge computing and edge intelligence. So we tend to think, you might think that we are talking mainly about the edge computing plane, that's true. But also we should keep in mind that the edge plane does not exist on its own. It exists in collaboration with cloud computing plane and the users. It processes the data from the users, so the user plane is an integral part. But then the edge plane is also wired to the cloud. And in many cases, when the edge resources are not sufficient, we are bringing some resources close to the end users, but these are still much less compared to the cloud resources. The scale is actually a couple of magnitudes smaller. So you will need to be integrated with the cloud computing plane as well needs to be integrated. And you will see that this is the architecture we use in many of our papers. Okay. Any question? No. Yes. Okay. Then this is also another paper of ours on vehicular edge computing. Vehicular edge computing is now again another form of mobile edge computing where the end users are vehicles, but it's not as straightforward. It's not a straightforward extension of the mobile edge computing scenario, because the speed of vehicle mobility is much higher, and that makes the environment much more complicated, much more dynamic, highly dynamic, and much more complicated. But this is also a model that has been accepted as a standard model. It's a paper from 2017. This has also been accepted as a standard model and has been followed in many papers afterwards. Yes, another leading study of ours on the use of AI and edge computing for the Internet of Vehicles. I would have liked to talk a bit more about it, but okay. Internet of Vehicles is the paradigm of connected vehicles, where vehicles can communicate with each other, with the infrastructure. So this is another paper, another leading paper that has been marked by Professor Wang, a IEEE Life Fellow, the editor. Okay, and now coming to the networks. This part is mainly on the use of AI for the networks. But before that, now we say I'm telling you that I'll be talking about a few of our papers where we make use of the AI technique. for solving certain problems in the network. But when I say that, the first thing that comes to our mind is what kind of data are we talking about when it comes to the network, right? And I'll give you two examples here where it's easier to relate, although that's not precisely the focus in the papers that I'll be describing. But for making the transition smoother, I'm giving you the easier to relate examples first. Now, see this vehicle, this has most of the vehicles nowadays have a lot of sensors, different kinds of sensors. They collect in a lot of data. Some of the data is processed locally. Some of the data is transmitted for edge computing or to the cloud in some cases. And with the objectives can be different, either for a simple application like collision avoidance or for self-driving, for example, or just to collect the driving patterns, to study the driving behaviors of a number of drivers. The intention, the purpose can be different, but there are numerous sensors that collect small amounts of data, like friction sensors or even optical sensors that collect images. But that's the kind of data that you analyze, for example, for vehicle safety or for autonomous driving, right? And you can relate to it. When we say data, this is the kind of data from different sensors, all right? And you can make use of this data to derive different parameters to estimate, to predict the position of the vehicle. Well, you can use GPS, but I'm giving an example here, to probably predict the next speed of the vehicle, the direction, probably trajectory, and so on. Now, another example, probably you want to predict the trajectory of this vehicle based on some historical data. In that case, a number of data points will be of interest: the historical trajectory, the current speed, probably also the source and the destination that you've got as the input from the vehicles, and a number of different things. You know, so in this case, also you can think of what can be the data that we are talking about that you need to process, that where you will be using the machine learning AI algorithms on. And the goal can be trajectory prediction, which can also help in congestion mitigation, traffic safety. And this is one of the very hot and happening topics as well in our area, where you talk about the prediction of the traffic. In some cases, the metrics can be different. In some cases, traffic density, in some cases, speed, in some cases, trajectory. But a lot is happening in this area as well. But it's easier to talk easier to think of and relate to the data that when we talk of such scenarios. Now, what happens? What kind of data are we talking about when it comes to networks? 1 second, I think I have another question here. Let me read it out. Would you say that having some of those technologies like smart grid, for example, rural microhydro connected to the grid, requires extensive upgrade of the infrastructure for countries like Nepal? Okay, that's one question. How do you see these state-of-the-art, at least the core idea, being applicable in settings like Nepal? Okay, yes, I think, Mahesh, would you mind if I keep that question, if I answer this question after we end this talk?
Yeah, sure.
I think,
sure.
Yeah, I'm running a bit late. Okay, yeah, but this is also a very good question in the context of Nepal. Yes, I'll come back to it. Okay. All right. Where was I? Yes. When it comes to networks, the kind of data that we are talking about is not something as easy to relate. For those who are not from the field, I mean, the way I understand the audience today is that some of you are from different backgrounds, but AI or machine learning, deep learning algorithms are the thread, the connection, the common point of interest. So for those who are not precisely from this background or from a related background, it might not be as easy to think of what kind of data we are talking about, and it might be a bit confusing when I talk about the next slide. So I thought I would include this anyway here. Now, we are looking into three different aspects: communication, computing, and caching. And when I talk about communication, the action space can be the mode of communication between a device, let's say this vehicle, and the base station, or between this device and the vehicle, between the households in the smart grid and the base station or the aggregators, for example. Different modes of communication, whether it is vehicle to grid vehicle to base station communication, or it's also called vehicle to infrastructure, V2I, or vehicle to vehicle communication, whether it is device to device communication between different devices, or device to infrastructure communication. These different modes of communication, that is the strategy, that is the action set when it comes to communication. So it's not precisely some data from the sensors in a vehicle or sensors in a device. You collect a lot of data from the smart meters, your electricity users, the electricity price from the market, for example, the state of the wind turbines. It can be different data. But when we are talking about communication, it's not precisely that data we are talking about, but the different modes of communication that we are talking about. Okay. Now, computing. When it comes to computation offloading and computing offloading is one of the areas, again, they're focusing on. In this case, how many tasks are you going to offload? Or it can be how many tasks are you going to offload to the edge server or to the cloud server? Or it can as well be decision making between processing your tasks locally and offloading it, 0 and 1. So that can as well be one of the things. Or a more complex but also commonly followed practice is that you offload a part of it, you execute a part of it yourself, another part by the RSU, and another part by the cloud. So these different these are the actions for the computation offloading perspective. And then even edge, it's not only one edge server, there are multiple edge servers, especially when it comes to vehicular networks. The vehicle is moving, so it will be in the coverage range of different RSUs over the time. So which RSU do you want to select, or should you select? That is another variable here. And that depends not only on where the vehicle is and within the coverage of within the coverage of mobile edge computing server 1 or 2 or 3, but it also depends on how loaded. What is the state of the computing server itself? Does it have a lot of tasks to complete before it can take your task? In that case, you might not want to offload it. There are different considerations to make. And that is closely related to one of the questions, I think, from Nissan, where you talked about the latency. You think that it has more resources, so you want to offload it. But eventually it turns out that it was full, nearly full. Even though you had less resources, you could have done it in a time less than what the edge server could have, for example. And these are the different variables to consider. Okay. And caching is storage. And most of the computer science people are familiar with the term. And that also means you request a certain data. How do you get them? From where do you receive it? Is it from the edge service you receive it? Is it from the cloud servers? Do you need to pull it from the cloud service? And that's from the vehicle's perspective, but also from the network infrastructure perspective, whether how should the content be placed and where? To the edge servers. So it would be, if possible, a very convenient solution if we can put everything in the edge. So whenever you need, you get it from the edge. But then that basically means you are moving the whole cloud to the edge, which is not a practical solution at all. The cloud was formed, cloud was made for a reason, and that stands as it is. But edge, the purpose of the edge is not to not to be the cloud. So which content to place and where, those are also the considerations that you need to make when you design a network. Okay. Yes. Now I would like to talk about this paper called Deep Learning Empowered Task Offloading for Mobile Edge Computing in Urban Informatics. And here we focus on edge computing and communication aspects. So computing and communication. In another paper, we also focus on caching. Here about 2 different aspects. There are key challenges when we talk about the vehicular networks. First of all, because of the highly dynamic topology as the vehicles are moving, it's not the static. You can, even when the scenario is static, even for the smart grid, is not always as trivial. That's why we need to design the optimization, resource optimization algorithms. You need to do a lot of smart things, put in a lot of smart ideas there. But when it's vehicular networks, it's much more dynamic. And on top of that, it's not only the vehicle speed that makes it more dynamic, but it's also the state of the multiple edge service. There are servers, edge service, multiple of them, many of them, and also their state. How much resources can they provide you at the moment? How much are they already occupied? And on top of that, when we are talking about communication, the V2X communication modes, whether you communicate in vehicle to base station mode, vehicle to vehicle mode, vehicle to some other device mode. So they are basically making your action space way bigger, you see. And on top of that, this is actually the first requirement, the QoS requirements. Latency is one of the crucial constraints here. whatever you need to do, you do whatever you need to do, whatever the network needs to do, but everything within 5 milliseconds or 8 milliseconds, provided the vehicles are moving, the dynamics is changing. So it's quite a challenging problem, actually. Now, in this particular paper, it's from 2018-19. Yes, from 2019, we look at the optimal selection of the service, and also optimal selection of the data transmission mode jointly, with an objective to maximize the utility of the offloading system under the latency constraint. Okay, yes. And this is the system, the scenario. I can see here where you have a number of RSUs. These are the edge servers here, here, and there's the computing capability of the server. You see, this is green, this is red, so and some other servers here. This is the Microsoft base station. That is also a server, one of the servers. It has quite large capacity, so this is good green, and this one is kind of blue-green. And what happens here is there are a number of base stations, number of vehicles. At different times, they will be under the coverage of these 3 vehicles are within the coverage of this RSU, and 1, 2, these vehicles are within the coverage of this RSU. Those that are not in the coverage of these RSUs, they will talk directly to the base station for the data that they need, for the tasks that they need to offload. And some vehicles, for example, this is not in the coverage of any of the base stations or RSUs, then it will rather have a V2V communication mode. So is the case for this one. Okay. Yes, these are 2 different communication modes, the spectrum assignment, but let me skip this. Now, the mobile edge computing server is modeled as a queuing system where the serving state of the server is the variable that may affect the choice, the selection of those servers. And we divide our analysis framework into a number of time slots, where what happens in the current time slot, which servers are selected or which communication mode you select, that depends on the previous time slot. So it's a Markov decision process, basically. But with the given state, the action and the state space, it's not possible to solve this MDP directly. So we use deep Q learning to solve the problem. And also I'd like to elaborate a bit on this, although briefly, why we want to use deep reinforcement learning here. What you choose as the algorithm that you choose, or the framework that you choose, that depends on a couple of different things. But reinforcement learning has been proven to be a viable tool for tackling real-time and dynamic decision-making problems. And that is precisely the case for networks here. And it has fared fairly well for solving complicated control and decision-making problems. And also allows the network entities to learn and build the knowledge about the network, the hidden patterns within the network, about computation, communication resources, caching resources, and to make the optimal decisions locally and independently. So that was one of our papers here. Now, in this one, this is from 2019 as well, we talk about computing and caching together. When I say computing and communication, we focus on computing and communication, or we focus on computing and caching. That does not mean the third part is not included. Computing, caching, communication, they go hand in hand. So it's not possible that you only work with 2 and leave the other one. That's not the case. What I mean when I say we focus on only 2 is those are the variables. But in this case, the computing part, computation offloading part, you have the variables that you can optimize over, and also the caching part, but communication is given. Okay, that's what it means. Yes, and the architecture that we propose in this case is quite well received as well by the researchers in the community. Here, this is the environment where you have a number of vehicles, the RSUs, which are the edge computing service. Again, the Microsoft base station, which has more resources than those RSUs. And this vehicular network, this whole network is the environment that for the agent, which is located in this base station, to learn. See, so the network is the environment, and the base station here, inside the base station, you have the agent that is learning from the environment. And there are a few peculiar things about this architecture that I would like to highlight. The base station, the agent that learns the behavior or regarding the demand of vehicles about the content. Here we are focusing mainly on the content content and computation. So what kind of content is being demanded, what kind of contents are popular, and so on. And the wireless channel conditions as well, that is learned by this agent here. Okay, a few other things about the architecture. For some reason, it's not synchronized. Okay, now see, this architecture is based on cross-layer offloading, which basically means this vehicle, when it has a computation-intensive task, the red vehicle has a computation-intensive task, this one, number one. It can offload the task to the RSU over here. And if the RSU does not have sufficient resources to execute that task, when I say sufficient resources, if there is no latency constraint, you can take probably longer time, but I'm also including the latency constraint. If you believe you don't have the sufficient time, then you can actually offload the task fully or partially to the base station here, which has much more resources than any of the RSU. And then the vehicle, this red vehicle, can get the result of the task executed after this has been processed by the roadside unit or the base station. And in some cases, it might, as depending on the type of task, it might as well decide to execute part of it locally and parts of the task either only by the RSU or by both. Okay, so in this case, this is called cross-layer offloading, 1 layer, 2 layers. But for this kind of cross-layer offloading, it's very important that the offloading decisions are made fast, and so are the resource allocation decisions for such computing tasks. Okay, this, see, from here to the RSU and here. Now, next specific feature of this architecture is cooperative multi-point caching and delivery, which basically means fast V2R content delivery. And here I'll give you an example. This yellow vehicle, B, that needs certain content from roadside, from RSU1, RSU2, and RSU3. That is what it has sent the request for. But this can be delivered by RSU1 when it is at this point, and by RSU2 when it is at this point, by RSU3 when it is at this point. For that, these three need to collaborate. This is called cooperative multi-point caching and delivery. But this also depends on another form of cooperative caching and delivery is that depending on the trajectory of this car, this vehicle, if it's traveling like this, then this is what will happen. But if it's only reaching up to RSU1 and then it has a different trajectory, it's not going to be the RSUs 2 and 3. In that case, RSUs 2 and 3 can actually transmit the content to RSU1, and RSU1 can send the data to this vehicle when it reaches the coverage range of the RSU. Since these are connected wires, so the delay in the latency in communication can be ignored. Okay, and the vehicle can get to the content from all of these RSUs through a single RSU. So that's also called the cooperative multi-point caching and delivery. The next feature is vehicle-to-vehicle edge caching. In some cases, the vehicles can also they can cache some data as well, and they can as well become the delivery points where relevant, depending on the latency constraints where applicable. Okay, yes, and we do utilize DDPG, deterministic policy gradient, to solve this problem, where this is the environment here, and the primary network and the target network. The primary network gets its input. State is one of the inputs. The current state of the vehicle. Vehicular network, current state of the environment, is one of the inputs. And the critic network gets its state from the training state and the action state from the replay memory, but also an input from the target network here, which is an older version of the primary network. Well, you have learned a lot over the past 9 days about machine learning, deep learning, including reinforcement learning, deep reinforcement learning. So we are basically applying this framework to solve this problem at the base station, by the agent at the base station. Okay. All right. This paper again, 1 hour 12 minutes. Okay, and all right. So here we focus more on the content placement and delivery. As I also said before, you might be it can be a bit overwhelming for the people who are not from the same background, when I talk about content caching, computation, communication, delivery, placement, many different terms, but it's not as complicated. It can just be overwhelming for the audience from a different background, but it's not that complicated, fortunately. The thing is, we did talk about how the content can be transmitted to different vehicles, and when the vehicles are moving, how it can be cached over multiple points, and how it can be delivered, how cooperation is essential and such. But one thing that we noticed here is that the time scale of content popularity and the speed of the vehicles, they are in very different time scales. You see, one of the primary factors, decision factors for placing the content. So it's a content caching and delivery, but in content caching, where exactly do you place the content? That's very important. Usually what the standard strategy is that in the networks, the content that's very popular, there are popular kind of content, less popular kind of content, big size content, smaller size content. But usually what we do is the ones that are highly popular, they are kept at the edge service, and the ones that are less popular are usually in the cloud. Less popular, less demanded are usually in the cloud. But also another important factor is that the content popularity changes over time. So it's not always the same content that should be in the edge servers. In that sense, even the content placement should be dynamic. Okay, but the advantage is that the content placement does not need to be as dynamic as the speed of the vehicles. These are two different timelines. So in this paper, we optimize content delivery and content placement and delivery jointly based on trilateral cooperation among macro cell base station, the roadside units, and the vehicles, the end users, which is I'll show you the architecture there. And this is a double timescale Markov decision process based on the fact that there are two timescales here. And this is a scenario, but this is a rather new, I think it's a paper from 2020. Yes. So it's a new scenario. It's not, this has not been studied much. We are one of the first few to study this scenario where, see, you have this vehicle. It's a content receiving vehicle, and this is traveling at different time slots, T1, T2, T3. It will be at different points. Here at the end of T1, T2, and then T3, it's here, and it moves on. But this is a content receiving vehicle. At this point, it receives certain content from this RSU, and at this point, it receives certain content from this RSU. But then from there onwards, now it can become a content caching vehicle, and it can deliver content to other vehicles that need the same content. So they don't always have to depend on the RSUs to get a certain content. Okay, 1 second. I think I see another question here. Is there any handoff strategies? It's a question from Suryaman Kolju. Is there any handoff strategies between two RSUs being applied for moving vehicles? Handoff strategies, you probably mean the coverage when the vehicles come within the coverage of different RSUs. So it's not precisely they don't need to do handoff as formally and officially, but what happens is as you move along, you can communicate with the RSUs. If you are within the coverage of the RSU, you will reach it, but if you are not, then you will not reach it. So it's as simple as that. It's on demand. When you need to communicate, then you communicate, or the RSUs can send you the signals when you are in the coverage range. Okay, and the between the RSUs, everything is wired, so that's something that we are not considering in this analysis. We are assuming that everything is taken care of. That's an assumption. Okay. Yes. So the content caching, the receiving vehicles can become, yes, good. Content receiving vehicles and the content caching vehicles, they can change dynamically as well. But this is although this is a part of the work that we have done, but it's quite challenging to make use of the vehicle resources. What we are trying to do is vehicles, they have limited resources, but they have some resources. So we are trying to make use of those resources also dynamically, but it's a scenario that's still evolving. Not much work in this scenario, okay? Yes, all right, I have some, okay, 13 minutes, so I'll try to be quick. In the third part, I would like to talk about privacy preservation and security considerations in the edge intelligence context. So what we did so far is that we talked about machine learning. We talked about deep learning algorithms in the context of the networks, and they bring in a lot of advantages, a number of advantages, like for any other domain in terms of computation computing, finding the optimal or close to optimal solutions in a distributed manner. Those are all the advantages, but it's only one part of the coin. Well, actually, it's not a coin. It has multiple facets, and another part is the privacy, preservation, and security considerations that we need to talk about, that we need to think about, consider when we talk about data. And it has become more and more crucial than ever to consider these aspects now that the privacy concerns from the end users are receiving the voice, and also there are questions on many platforms, including Facebook, the way data is handled by these big players, and the data security measures, how secure is the data. So it's high time really that we all think of not just the data and using the data, but also how sensitive is the data, how secure is the data sharing, and so on. Okay, in this section, I would like to very quickly talk about probably three of our papers, but I'll walk you through very quickly. Now, see, in this case, this is a paper on data privacy preservation in vehicular systems, and we use federated learning in this case. There are different scenarios, many scenarios. Data privacy preservation and data security is as important in every field, in every research area. I chose to introduce this paper because vehicular cyber-physical systems, vehicular networks, is a very interesting use case, because you are generating a lot of data at the edge. You are making use of the data. You're transmitting it to the edge servers. That also means you are opening up venues for the adversaries to eavesdrop, to tamper, to get the data, to tamper it, to tamper for the results. You see, you're basically opening up the venues. You're not keeping the data for yourself. You're generating data or collecting data, and you are actually sending it somewhere, right? And that means the venues for data leakage are open at multiple points. It can be sensitive information. It can be very important information. But then when that happens, if the data leaks, it's not only the digital consequences that, okay, the packet didn't reach or the packet was modified, so the vehicles did not get the best possible signal, the signal for a best possible trajectory. For example, there is congestion here, so you follow the other track. It may or may not be very serious in that case, but the consequences are far from digital consequences. In this case, it can be more than economical consequences. It can endanger passenger safety, not to mention privacy even. So the consequences can be really grave. So it's a very interesting case study, although I do not have time to talk in detail about this. But briefly, this is a scenario we consider here: end users, the edge service, and then you are transmitting the data from the end users to the edge service. So the adversaries can get your data from here, or also from here, they can receive the data or tamper the data. Different points here where the adversaries can eavesdrop and launch attacks. In this case, we use federated learning. So that's not a strong contribution in itself. Federated learning is a kind of, I'm not sure if you have had any lectures on federated learning. I saw that you have had lectures on reinforcement learning, deep networks, deep neural networks, but federated learning, the concept, let me just explain the concept. Federated learning is a kind of distributed machine learning, although when you say distributed machine learning, the focus is slightly different. But these are the users that have some data of their own. And if you transmit this data, usually, okay, sorry, what is happening here? I have no idea. Yes, usually you transmit your data, and then somewhere at the aggregate, an aggregator or a server collects the data from all of you and then does model training on it. But in federated learning, you don't want to transmit your data. It's a privacy sensitive, privacy aware learning machine learning, where you keep the data to yourself and you train the model based on your own data, but you exchange the model parameters with the curator or with the server, and the same with other users as well. Based on the input from all the users, the server will generate a global the weight factors, and it will update the individual users with those parameters, but they will train again based on their data. So this iterative process will eventually lead to a global training model without sharing of the data of each user. That's the idea of federated learning. So it's not a strong contribution in itself, but an advantage, the default advantage of federated learning is that privacy is preserved to some extent because you're not transmitting the data. You're just keeping it to yourself. You're only transmitting the model parameters. Okay, but this is the conventional structure of federated learning that I just explained. The model parameters are exchanged with the curator over here. But in our case, it's not only the conventional federated learning. What we also do is that we use the method of we also distort the model parameters. So it's a scheme called differentially private model distorting, and we use random sub-gossip updating between the vehicles. We don't utilize a central curator because the curator can as well be tampered, or it can as well be a single point of failure. So the global model is found by random gossiping between these vehicles. It's a peer-to-peer vehicular federated learning scheme. All right. Okay. Next is on data poisoning attacks. I think many of you have heard about the crowd sensing systems, where the sensors or the ones data generators are not the dedicated part of the infrastructure, but they are the normal people with devices that can send you data. And here in this paper, we try to look at the other side from a malicious user or an adversary perspective, where you try to attack a system. You try to actually launch a data poisoning attack in a crowd sensing system. But would it be possible to launch the attack? That's what we study in this paper. And we show that the attacker can also learn to attack in such a way that you cause harm to the system, but at the same time remain undetected for quite a while. So this is a completely different perspective. Just like the two sides of the coin, machine learning brings in a lot of advantages when you can make use of the data for altruistic, for non-malicious users, for the system, non-malicious system. But at the same time, it's from the adversary point of view, you can also make use of the same approaches for learning about the system and actually to launch attacks that can cause harm of different levels. In this case, we use an application called TruthFinder. TruthFinder is an application based on crowdsourced crowdsense data that creates people's profiles and such. And here, in this case, there are a number of workers, the normal workers who are not malicious, and some malicious workers, and they try to provide the wrong data, false data to the TruthFinder. Okay, I'm sorry about this switching of the slides. But what they do here is they do not, if they provide very different data than the normal workers, then of course it would be easy to detect them. TruthFinder constantly provides feedback to those, to all the workers. The crowd sensors are called the workers. The TruthFinder will provide certain rewards or certain punishments based on how similar or how different your data is with the rest of the crowd. So you cannot really launch a very big attack at once. But the goal of the attacker here is that you make small changes or you poison the data slightly, and then you stay there in the system for long. And for that, what helps the malicious workers is the TruthFinder itself. In this scenario, the malicious worker is actually the agent, and the TruthFinder is the environment from where it's getting the feedback. So if you're getting the scores that are really less, then you probably try to reduce the weight of your injection, and if not, you try to gradually increase it. And we show that it is actually possible to launch an attack like this. All right, this is the final paper. Okay, 3 minutes. Called Protecting Machine Learning Integrity in Distributed Big Data Networking. So I did talk about federated learning, but here I talk about distributed machine learning, distributed big data networking and machine learning. And although federated learning is also a form of distributed learning where you don't accumulate the data for learning in one place, but with federated learning, it's more of decentralized data and decentralized distributed learning. In this case, when you talk about distributed machine learning, the data can still be centralized, but the learning is distributed. And the focus is slightly different. There in federated learning, the focus is on privacy preservation, and not sharing the data at all. But in this case, what actually happens is when it comes to big data, very big data, then usually it's possible, if it's possible, to divide those data, divide the data into chunks and provide it to different nodes in the network where the data can be processed parallelly. This is actually a method of, you might as well have had a lecture on distributed machine learning. I'm not sure, but this is a method of addressing the computational limitations of machine learning algorithms when it comes to very big data sets. So you divide the data into different, distribute the data to different nodes and try to make use of the computing capacity of all these nodes to process the data, analyze the data parallelly. That is distributed networking. So the focus here is not precisely privacy and decentralized data, but it's more on scalability and computational efficiency. Okay, but in this case, when you are dividing the data to and distributing it to different nodes, what's important, protecting the integrity of the data becomes even more important. It is important for all the kind of data. In this case, it becomes even more important. And we propose a secure architecture, first contribution in terms of the architecture itself, and we also propose two data tampering detection schemes for protecting the integrity of the data in this case. These are two different kinds of systems called the N data-oriented system and the center data-oriented system, where we talk about two different kinds of threats. The first one is from the data source here to the distributed learning nodes. These are called the workers that train the model. And here the adversary can tamper the data here. But at the same time, also, even if it does not tamper the data here, the workers can be compromised, the workers can be attacked, and also, even if both are not the case, the result over here can as well be tampered. So there are different points where the tampering can come in. And this is the center data-oriented system where you start not from the end devices, but from the workers, but there are also a number of different points, vulnerable points for the attacker. Okay, and this, yes, so these are the three different types of threats possible, and we model this system as into three layers: the data source layer here, the distributed learning layer here, and the aggregation layer here. And what we do is we use the hash and sign method. You generate a hash and sign the hash, and you transmit it along with the data to the distributed learning layer. And distributed learning layer does the same when it transmits the data to the aggregator. So even if your data is tampered, it's actually possible to detect the abnormalities, as you will see here. Detect the abnormalities, and in fact, there are two different schemes, but in one of them, it's also possible to locate and remove the malicious users. Okay. Yes, I think I would not like to, I wouldn't present more papers than that. I think that we also, it's 1 hour, 31 minutes. But very briefly, the conclusion, what I did today is I presented energy informatics as a research area that we are working on that encompasses smart energy systems, communication networks, computing networks, including caching, of course. We learned about AI as a tool to capture, learn, and characterize the hidden patterns of the heterogeneous, dynamic, and complex networks. But not just that, we also learned about edge networks. When I say edge networks, not edge networks standalone, but the end-edge cloud orchestrated architecture as an enabler for machine learning in general, in particular with a focus on distributed machine learning. And we also discussed about the other side of the coin, the privacy preservation issues and data security, secure data sharing mechanisms in the edge intelligence scenario. And I hope by the end of my talk today, I have been able to give you some ideas on what are the different topics, especially for those who are looking for their master's thesis topics or probably some interesting bachelor's final year projects, or maybe even those of you who have just started your PhD. You've found some interesting areas to work on. I've made you aware of hot and happening topics in our area. And you've learned a lot about machine learning already, but my objective of my talk today was to give you an idea of its applications in the network and also network as an enabler for AI. And I hope you've got some of those some of the interesting ideas in your head by now. Okay, thank you very much. I would now like to open up. I'd be glad to take your questions. I'm not sure how much time we have for questions, but at least I would like to take a few. Yes, I see some questions here, but let me start by answering the question from Maheshi. Okay, if you don't mind. Yes, Maheshi's question, let me read out loud again. Would you say that having some of these technologies, smart grid technologies, for example, having rural micro hydro connect to the grid require extensive upgrade of the infrastructure for countries like Nepal? And how do you see the state of the art being applicable in settings like Nepal? Okay, that's very good and also a very big question. Well, the answer is not that straightforward, but yes, some level, the easiest answer or the shortest answer would be some level of upgrade is certainly necessary, I would say. Yes. Not only in Nepal, actually in all over the world, also in all countries, even in Norway, the upgrade was necessary. But then this is not something that happens overnight. And when I say upgrade is necessary, that does not mean you need to change the whole infrastructure. You have the infrastructure already for the power infrastructure already in place, but you are adding communication infrastructure on top of that. But that does not mean you are adding a completely new infrastructure on top. What we are talking about here is we have 4G networks, now 5G is being rolled out gradually. Maybe after 10 years, 2030, we'll be talking about, hopefully, about 6G. But these communication networks, in particular the wireless networks, as the communication networks are upgraded, you can make use of a huge part of it for different applications, including the smart grid. Okay, but on the other hand, it's not only the being a free rider and taking the advantage from those networks that will be deployed anyway. That is not the case either. You will have to upgrade your infrastructure. For example, the simplest example I can give you is in Norway. Also, I think it started in 2015, and I think it was completed by 2018, or maybe it started in 17 and completed in 19. They replaced all the smart meters in individual house, all the conventional meters in the individual households by smart meters. In each and every household, they came and installed the smart meters. But the provisioning for connecting the smart meters to the communication infrastructure, to the networks, they use a very simple technology for communication, the smart grid. That was taken care of. That was done. That was done manually in each and every household. So those kind of updates need to be done. And also, when you can add, you will need to add sensors in the distribution network for automation or for semi-automation. There will be different levels of automation, but you need to add sensors there. And it's not only adding sensors. When you add sensors, then you need to proportionally upgrade your infrastructure also for operation and control, for monitoring, for analysis. You need to add some service probably. Or what is also happening is you are buying services from publicly available cloud services, and that is also one way to do it. That varies between countries, between governments, but yes, some update would be necessary, but at the same time, you can also make use of. And that's where the role of the communication networks, the cellular networks, those things come in. Okay, Maheshi, did I answer your question completely?
Yes. Yes.
All right, good. Okay, now I'm hearing my echo again. It's probably from that side. Yes, good. Yes, now I have a question here from Avinash Karmacharya. Avinash, you're asking, can edge computing or any other advanced algorithm be used to tackle grid-related problems such as reactive power supply due to penetration of electric vehicles? If so, how is it better than existing control systems? Okay. Hmm. Can you use edge computing for tackling this problem? And how is it better than the current systems, current solutions? Okay. Yes. Okay, let me go back. I think for answering your question, Nashri, I'll take you back to a slide somewhere here. Maybe this one, both of them actually. Yes. Yes, edge. Yes and no, probably both of them. In this case, you want to tackle reactive power supply because electric vehicles, yes, it's everything that we talk about, whether it's a new technology or a new algorithm, they all have two different sides, and it's our very natural tendency that we often talk about only one side of it. But thank you, Nashi, for bringing this up, because electric vehicles, they bring in a lot of possibilities within the smart grid ecosystem in terms of storage, not just storage, but mobile storage. And also they save a lot in terms of the pollution created by the in reducing the pollution created by the transport sector. So those are very big advantages, and electric vehicles are seen as one of the most important enablers of the green urban revolution, in fact. But at the same time, when you introduce electric vehicles, at a time when we are already struggling with many problems even with the conventional use of the power, such as peak load, and we are introducing ideas, concepts such as demand response management, where you try to incentivize the users to use less power at certain times, peak hours, or when you are using, or when you are trying to distribute them. Some users use it at this time, some users use it at that time. There are a number of different incentive mechanisms, in fact, where you also, in some countries, like in Australia, they also had the scheme where they actually paid the consumers for using electricity. Not that you pay, but the operators pay you for using the electricity at times, certain times. So there are different forms of incentives, and you need to balance the grid. The grid, it operates at a certain frequency, and the supply and the demand, the total amount overall, supply from the grid and the consumption should actually be always equal. If there is a slight mismatch, then you need to observe the power. You need to turn on the loads that you actually don't need to. Different things to do. But at such a time, when the grid is already in some sense overstrained, when you're introducing electric vehicles, then you are straightforward adding a lot of weight to the already strained grid, right? So what you're basically doing is you are also trying to optimize, optimize the power flow, make the grid more balanced, and reduce the peak hours, which will help you bring down the investment in the grid for next 10 years, 15 years. But at the same time, you are introducing electric vehicles, so that will definitely take your peak hours even further up. Unless and until you have your generation facilities are upgraded considerably, that it's likely that, depending on the country, in Norway, it's a very special case, because we use a lot of hydropower, and the Norwegian power infrastructure that has been operating at a slightly lower level than its actual capacity. So in that case, it may not be as difficult, but in some countries where the grid is already operating at a very close at a level very close to the capacity, it might not be that easy. It might in fact be quite a degrading solution or idea as well. Now, in such case, and now coming back, this was to provide the context. But now, in such case, can edge computing be used? See, and how is it better than the current control systems? There are two things to this question of yours. The first part is, yes, edge computing can be used. Okay. But when I say edge computing can be used, it's mainly about generating certain data from the edge, which in this case would be the electric vehicles or the households, and also some communication between the electric vehicles or between households as a community. That would be the part of the edge computing. So you can collect certain data, and that data can be used, for example, to derive certain patterns, the charging patterns. This is a very important problem. We have actually two of our master students, they have done some work on the charging infrastructure design. The driving patterns, the use of not just the driving patterns, but the electricity users pattern, and that's closely related to the driving pattern. Okay, the fuel consumption, that part, and when and how do you charge? Do you charge it mostly at night at home, or do you go and charge it in the charging infrastructure? Do you use fast charging? There are 3 types of charging. So what kind of charging do you use mostly? Or today, is it going to be different? So that kind of data can actually be collected from from the edge, from the end devices, and that can be utilized, that can be analyzed at the edge itself, for example, by the charging infrastructure, let's say, okay? Or also by the vehicles themselves, when there are different kinds of problems that we are looking at, where you say, okay, how do you optimize the operation of a charging infrastructure? Or how do you minimize the queuing for the vehicles in a charging station? These are different problems, but the data that you collect for these problems, that is the utility of the data that can tell you more about the user patterns, charging rates, and that can be made, that data can be utilized also for better planning and better infrastructure design, or for infrastructure capacity design on the network side, on the grid side, on the other side. Okay, so in that sense, yes. But then if you ask me how should this be better than the current control systems, that I cannot answer completely. I can say that it will help with this data in the design of the control itself, but whether or not it will be better or not, I cannot answer that completely. Also partly because it has nothing to do, I'm not talking currently about the control solutions themselves, but I'm talking more about the data and the utility of data, which can play a role in the design further. But the solution for the reactive power itself, reactive power supply, how will that be better? That is a completely power system thing, which is unfortunately not my expertise areas. We are not focusing on that part. But with my humble opinion is that, although I'm not an expert in that area, my humble opinion would be that it shouldn't change the control strategy itself, but it will play an important role in the planning and design part. I hope I answered your question, Avinashi. Yes, great. Thank you. More questions?
I think if we don't have any more questions in the chat, and also I do not, right, so if we do not have more questions from the hall too, then probably we should go towards wrapping up the session then.
Yeah, sure. Yes, and you have my contact details here if you want to know more about my work. This is my homepage. You can go and take a look, or if you have more questions about my work, or the presentation today, even other questions, you can email me. Okay.